Good day, everyone. This is Claire Margaret C. Dasig of CM113P, Section A14. Today, I will solve 4 problems regarding atoms, molecules and ions, quantum theory, electronic structure of atoms, periodic relationship among the elements, and the basic concepts of chemical bonding. First, we have here problem 2.18. Write the appropriate symbol for each of the following isotopes. Letter A, C equals 74, A equals 186. Letter B, C equals 80, A equals 201. We recall that in writing isotopes of any element, it can be represented as this. X is the atomic symbol of the element. A is the mass number, and Z is the atomic number. So we're just going to substitute this given in this representation. So place letter A or the mass number as the superscript. A is 186. And letter Z or the atomic number as the subscript at the left side of the atomic symbol. So Z is 74. So for the atomic symbol, since we have the given 74 as the atomic number, we can easily find the element in the periodic table. Here we can see that the atomic number 74 is element tungsten. The symbol for tungsten is W, so we write it here. And here we go. This is the appropriate symbol for this isotope. Next, letter B. We're just going to apply what we've learned from the previous letter. So place the mass number as the superscript, 201, and letter Z or the atomic mass as the subscript. Okay. For the atomic symbol, just take a look at the periodic table and find the atomic number 80. The element is mercury. So we write the symbol Hg. So this is the appropriate way of writing isotopes. Next, problem 7.76. The ground state electron configurations listed here are incorrect. Explain what mistakes have been made in each and write the correct electron configurations. We all know that electron configurations of any atom is the representation of the arrangement of electrons distributed among the orbital shells and subshells. So there are 4 types of subshells. S, P, D, F. S, P, D, F. So here, S has 1 orbital shell and can hold up 2 electrons. P has 3 orbital shells, can hold up to 6 electrons. D has 5 orbital shells and can hold up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. For F, 1, 2, 3, 4, 5, 6, 7, 7 orbital shells can hold up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons. In the periodic table, the first two, and the helium are the S block. Noble gases, halogens, nonmetals, semimetals, and other metals at the opposite side are the P block. The inner transition metals are the D block, and the lanthanide and actinide metals at the bottom are the F block. This is the order that we follow for electron configuration. So, going back to our problem, 1s2, 2s2, 2p4, 3s2, 3p3 is the electron configuration given for aluminum. Aluminum is part of the P block, and its atomic number is 13. Since this electron configuration is in ground state, no ions is indicated. One way to see if the electron configuration of an element is correct by comparing its atomic number and electrons. So if we add here the electrons, 2 plus 2 plus 4 plus 2 plus 3 is equals to 13. It's the same. So what is the problem here? If you analyze the electron configuration thoroughly, we did say that P block or P subshell contains 3 orbitals, meaning to say it can hold up to 6 electrons. If you see it here, this part 2p4 is incorrect. So to write the correct electron configuration, Al is 1s2, 2s2, 2p6, 3s2, 3p. As I said earlier, we can add the electrons here to compare with the element's atomic number. So if you add 2 plus 2 plus 6 plus 2, we get 12. So we only have 1 electron left for 3p. So we put 1 electron. So this is the electron configuration of aluminum. Next, we have boron here. It says that boron's electron configuration is 1s2, 2s2, 2p5. The atomic number of boron is 5. This part here, 1s2, 2s2, is correct, since S subshell can hold up to 2 electrons. But the last part here, is incorrect because if you add up all the electrons here, 2 plus 2, the number exceeds compared to the atomic number. So, the correct electron configuration of boron is 1s2, 2s2, 2p. Since 2 plus 2 is 4, there is only one electron left, so this would be 1. The correct electron configuration of boron is 1s2, 2s2, 2p1. Last, we have fluorine, 1s2, 2s2, 2p6. Fluorine's atomic number is 9. If we add up all the electrons here, we get 10. 2 plus 2 plus 6 is equals to 10. So we have an excess electron. If we check the S subshell, this is correct since S subshell can hold up 2 electrons. So 2p6 is the problem. Since we have one excess electron, we're just going to subtract it so that we can get a total of 9 electrons. So the correct electron configuration of fluorine is 1s2, 2s2, 4, so 2p, 5. If we add it up, 5 plus 2 plus 2 is 9. So this is the correct electron configuration of fluorine. Next problem, 8.51. Arrange the following in order of increasing first ionization energy: sodium, chlorine, aluminum, sulfur, and cesium. So first, ionization energy refers to the amount of energy needed to remove an electron from an atom. I have here the table that indicates that the ionization energy increases from top to bottom, in groups, and increases from left to right across the period. So we could identify the location of these elements first. Na is here, Na, chlorine over here, aluminum is here, sulfur, and cesium. As you can see, cesium has the lowest ionization energy among the elements, so it comes first. Then we go up, so you can see, go up at the periodic table, and we can see that sodium, aluminum, sulfur, and chlorine are in the same period. We know that ionization energy increases from left to right, so we're just going to write it here. Cesium, okay, sodium comes next after cesium, then aluminum, sulfur, and chlorine. Therefore, we can conclude that cesium has the lowest first ionization energy among the 5 elements, and chlorine is the highest. Lowest, highest. For the last problem, we have 9.51. Write Lewis structures for the following ions. So first, we have letter A. So first we have here letter A, NO2 plus, or we could say that this is nitronium ion. So first, calculate the valence electron. Nitrogen has 5 valence electron. Oxygen is 6. But since we have 2 oxygen, multiply this by 2. And we have a positive charge, meaning to say we lose an electron. So that is -1. Total of 16 valence electron. So since nitrogen has the least electronegativity among them, it has to be at the center of the Lewis structure. Okay, so oxygen goes at both sides. And don't forget the negative, the positive charge here. So nitrogen has 5 electrons, so 1, 2, 3, 4. But since we have a positive charge here, it loses 1 electron. Oxygen has 6, so 1, 2, 3, 4. But we know that oxygen has two lone pairs, so 1, 2. Total of 6 valence electron, same as the oxygen here. 1, 2, 3, 4, 5, 6. So we just bond it here, here, and there you go. This is the Lewis structure. O, double bonded N, double bond O, and the lone pairs. Don't forget to charge. Okay. So for the formal charges, we could use this formula equals total number of valence electron of that element minus the non-bonding electrons minus bonding electrons over 2. So here we can compute for oxygen, we have 6 valence electron, then 4 non-bonding because 1, 2, 3, 4, the lone pairs, 4 non-bonding, and 4 bonding as well because 1 bond is equivalent to 2 electrons. So that is 1, 2, 3, 4, 4 bonding electrons over 2. So we calculate this, we get 0 charge. So we put this here. So in this side, the oxygen in the right side, oxygen has 6 valence electron. Same as the first one, we have 1, 2, 3, 4, 4 non-bonding electrons and 4 bonding electrons as well over 2. 0 charge. 0. So, for nitrogen, nitrogen has total of 5 valence electron. We can see here that nitrogen has no non-bonding electrons, so we put 0 here. And then calculate the bonding electrons. So 2, 4, 6, 8, a total of 8 bonding electrons over 2. So we get 1 charge, 1 positive charge. As you can see, we have 1 here. So the formal charge of NO2 plus is positive 1. So next, for letter B, we have S2, 2 plus 2 negative. So we calculate again the valence electron. We have 6. Sulfur has 6 valence electron times 2 because we have 2 here. Then since we have a negative charge here, negative charge means it gains electron. So plus 2. So a total of 14 valence electron. So here you can draw the structure S. As you can see, since we have 2 negative charge, we can put S here, S negative, S negative. So since S or sulfur have 6 valence electron, we put here 1, 2, 3, 4, 5, 6. And since we have here positive charge, we add another electron. Same goes here. 1, 2, 3, 4, 5, 6, 7. So connect and we form a single bond. So the Lewis structure is S, bond to S, 1, 2, 3, 4. Don't forget the lone pairs. And we can say that we can combine the charges and 2 negative. So for the formal charge, we will use again the formula before. So for sulfur, here, the left side has 6 valence electron minus how many non-bonding? 2, 4, 6. 6 non-bonding electrons and 2 bonding electrons. 2 over 2, we get negative 1. So here at the right side, 6 valence electrons since sulfur has 6. How many non-bonding? 1, 2, 3, 4, 5, 6. 6 non-bonding electrons and 2 bonding electrons over 2, we get negative 1 as well. So we can say that, we can check it here. So we could say the formal charge or the total formal charge of S2 to negative is negative 2. Next, we have letter C, given is Br, bromine, F, fluorine 2 plus. So, again, we calculate the valence electron. Since Br and F is in group 7, so the total valence electron is 7. 7 plus 7, and we have 2 here, so we multiply by 2, and positive charge means say they lose electrons, so negative 1 minus 1, so 7 times 2, 14 plus 7 minus 1 is 20 valence electron. So we can start drawing the Lewis structure. Pr at the center because it has these electronegativity, F at both sides, and don't forget the charge as well. So Br has, or bromine has 7 electrons, but we lose 1, so total of 6, 1, 2, 3, 4, 5, 6. For fluorine, we have 7, 1, 2, 3, 4, 5, 6, 7. And same here, 1, 2, 3, 4, 5, 6, 7. So connect, bond it together. So this is the Lewis structure. F bond PR. F, forget the charge and the lone pairs. Okay. So for the formal charge, again we apply the formula. So fluorine at the left side has 7 total valence electron minus how many non non-bonding electrons? 1, 2, 3, 4, 5, 6. So 6 and 2 bonding electrons over 2. So that is 0. So you have here the center, bromine, again have 7 valence electron, and non-bonding 1, 2, 3, 4, 4 non-bonding electrons minus 1, 2, 3, 4, 4 bonding electrons. So that is 1. For the fluorine at the right side, it's just the same. 7 valence electron. 1, 2, 3, 4, 5, 6. 6 non-bonding. And 4. Oh, 2. Wait, 2. 2 bonding since single bond. That is 0. So we can conclude that the formal charges of BrF2 plus is positive 1. Last, we have letter D, Sc, and negative. So first we calculate the valence electron. So sulfur has 6 valence electron because it belongs to the group 6 plus 4. This carbon has 4. This nitrogen has 5. Since we have a negative charge here, put plus 1. So a total of 16 valence electron. So you can draw the Lewis structure S, C, and we put the negative here because nitrogen has more electronegative than sulfur. So valence electron of S is 6, 1, 2, 3, 4, 5, 6. Carbon is 4. And nitrogen is 5. Since we have a negative charge here, we add 1. So connect. So this is the Lewis structure of Sc and negative, SCN. Don't forget the lone pairs and the charge. So for the formal charge, we apply the formula before. So sulfur has a total of 6 valence electron and 4 non-bonding electrons. Then sulfur has also 4 bonding electrons over 2. That is 0. Next is carbon. Carbon has 4 total valence electron minus 0 since it has no non-bonding electrons. Then 2, 4, 6, 8. 8 bonding electrons over 2. So that is 0 as well. So for the nitrogen, 5 valence electrons minus 4 non-bonding minus 4 again bonded or bonding electrons over 2. So that is negative 1. Therefore, you can say the formal charge of Cn negative is negative 1. So that's it. Thank you for listening and keep safe.